Hello everyone. In this video, we will derive the Euler-Lagrange equation. Euler-Lagrange equation. We'll derive the Euler-Lagrange equation. This is the simplest derivation of Euler-Lagrange equation, in which the only thing that you need to know is Taylor expansion of in multiple variables. So let's say there are three variables. We are going to write it as, let's just take two variables, x plus delta x, y plus delta y. The Taylor expansion of this quantity is going to be f of xy plus partial derivative of f with respect to x calculated at the point xy times delta x plus partial derivative of f with respect to y calculated at the point xy times delta y plus higher order terms. So this is the Taylor expansion of a function in two variables, and we will only need this quantity to derive the Euler-Lagrange equation. Now, to do the Euler-Lagrange equation, we will do it for a dynamical system. We will use what is called the Hamilton's principle. Hamilton's principle. Okay. So what is Hamilton's principle? Hamilton's principle says that if, let's say there's a dynamical system. So if there is a dynamical system, So let's say we have a dynamical system that goes from point T1 or at time T1 to T2, from point X1 to X2. So the dynamical system is defined as x of t, where x gives the position of the system at time t. Let's say the system goes from point x1 t1 to x2 t2. So there's a dynamical system x of t that goes from point x1 at time t1 to x2 at time t2. Then the path that the system takes, So while the system goes from x1 t1 to x2 t2, there are multiple paths that it could take. It could take this path or this path or this path. So what path is it going to take actually? And Hamilton principle says that if the system goes from point x1 t1 to point x2 t2, the path that the system takes is such that there's an integral called the action integral. The action integral, which is defined as t1 to t2, L of t x dot, where x dot is the velocity, dt. So this integral is stationary. S-T-A-T-I-O-N-A-R-Y, stationary. Okay. So of all the possible paths that the system can take, the path that system will actually take will be such that this integral is stationary. And by stationary, it generally means a maximum or a minimum. So mathematically, let's say that the object or the system took this path. So as the object goes from x1 t1 to x2 t2, this is the actual path that it takes. Then the being stationary means that if there was a different path which is infinitesimally close to the first path. So let's say there is a different path which is infinitesimally close to this path. Then if you calculate the action integral along this new path, so we have the original path, so we can calculate the action integral or in the original path or the actual path, and then we can also calculate the action integral along this new path. And if you look at the difference between, the new path and the actual path or the original path, that difference is going to be zero up to the first order. Up to the first order. Okay, so that's the meaning of being stationary. And we are going to use this idea to derive the Euler-Lagrange equation. So how do we do that? Now we are interested in this integral action, which is t1 to t2 L of t x x dot dt. Now this integral is being calculated over dt from t1 to t2. So we all know that an integral is, we can think of an integral as the area under a curve, right? This is another way of thinking about what an integral is. And we are interested in calculating the integral L of dt, L of t x x dot times dt from t1 to t2. So this area, which we are interested in, we can also calculate this area by dividing this area into small parts. So let's say we divided this area into small parts, where each one of this part has the length epsilon. That's how we are going to divide it into multiple parts. And then the integral can be thought of the area of each one of these individual parts summed over. So this integral A we can write as a sum over I equals 1 to n of each one of these small parts, okay? Where the area of these parts, so let's say we are looking at this part, the area of this part can be thought of, let's say this is T1, T2, Ti, so on up to Tn. So we divide it into n parts where we have Ti as one of these points. Then the area of this part would be this width, which is epsilon, times the value of the function calculated at this point, Ti. So we can write it as L of Ti x calculated at the point I, which would be xi, and x dot calculated at the point I. And then multiply it with the width of this area, which is epsilon. Okay, so this is also another way of writing this integral in the limit that epsilon is very, very small. So this area can be essentially calculated as the area of a rectangle. So each one of these parts can be calculated as the area of a rectangle. We sum them over all of them, and then that gives us the action integral. Now, we can go one step further. So I equals 1 to n. Let me write epsilon first. The L can be written as Ti, xi. Now, x dot is speed or velocity. Now, velocity can be written as x of I plus 1 minus of xi divided by t of I plus 1 minus ti, right? That is just the definition of velocity. Now, ti plus 1 minus ti is simply epsilon. So I'm going to replace this with epsilon. So now you can see that this area depends on L of Ti, xi plus 1, and xi. So these are the things that this area depends on. Now, what we are interested in is, according to Hamilton's principle, if we change the area, if we change the path that connects point x1, t1 to x2, t2 by a small amount, this action is not going to change, okay? So we are going to do that. We are going to change this path, but we'll do it in such a way that our that it's very easy to calculate what is the change or what is the change in the area. So we can take the difference between the original and the new path. So let's do that. And we'll do it in this way. So we know that this action integral depends on the point ti, xi, and xi plus 1. These are the only points, or at least one, this term depends on only these 3 points. So what we are going to do, let's focus on this point xi. And I'm going to expand this. So this is point xi. We have xi plus 1, xi minus 1. And of course, then we have the rest of the curve. So we'll have the rest of the curve, but we are only focused on this point xi for the time being. And one way of changing the path from the original path to a new path is by moving this point xi. So let's say we move this point xi by some small amount delta x. Okay? So we are not going to affect the rest of the curve. Every point in the rest of the curve remains exactly the same. We are only changing the point xi. By changing this point by xi, we have caused these two segments of the area to change. The rest of things remain exactly the same. By changing the point xi, if we are calculating this area integral, only these two triangles, so if we are changing here, you will see that rest of the area remains exactly the same. Only these two parts will get affected. Okay. Now, since only these two parts get affected, the change in area is essentially going to be this part. The rest of it is going to be exactly as the original integral that we are interested in. So only this part will be our change in A. Change in A, which is A mu minus A actual or original, is going to be this red part. The rest of it is going to be exactly the same. That's how we can get the change in A. So we are going to calculate this change in A, and let's do it this way. Now, we also realize that if we change only the point xi, two terms in this sum get affected. Although only one point is being changed, there are two areas that get modified. One of the areas that get modified is from xi and xi plus 1. The other one that gets modified is xi minus 1 to xi. And the reason is because if you change the point xi, there are two places where this point appears. One is in the ith term, where you will get xi plus 1 minus xi, but also in the I minus 1 term. So the I minus 1 term of this sum will look like L of ti minus 1, xi minus 1, comma, xi minus 1 over epsilon. So the I minus 1 term also has an xi. And because the I minus 1 term has an xi, this term also gets affected apart from the xi term. So we are interested in what is the difference between the new path and the original path or the actual path. So because the new path there are only two places where the new path and the original path will differ. This would be the I minus 1 term and I term. We are going to only write those terms. The rest of the term we have already taken care of because they are exactly the same. So when we take the difference, they all cancel out. The only term that remain are epsilon L Ti xi plus 1 minus xi over epsilon plus epsilon L of Ti xi Ti minus 1 xi minus 1 xi minus 1 over epsilon. These are the two terms are coming for the new path. And then we will have the two terms from the original path would be L Ti xi plus 1 minus xi over epsilon plus epsilon of L Ti minus 1 xi minus 1 xi minus xi minus 1 over epsilon of the original path. Okay, and just to differentiate between the new path and the original path, what I'm going to do is as we change the point xi to xi plus delta x, we are going to, in place of wherever we get xi in the new term, we are going to replace it with xi plus delta x. So if we do that, this becomes epsilon L of Ti xi plus delta x, comma xi plus 1 minus xi plus delta x, so because there's a minus sign, you will get a minus delta x over epsilon plus epsilon times L of Ti minus 1, x of I minus 1. Then you will have a xi plus delta x minus xi minus 1 over epsilon. And then the two similar terms from the original part. So you will have x of L Ti xi plus 1 minus xi over epsilon minus epsilon of L of Ti minus 1 xi minus 1 xi minus xi minus 1 over epsilon. Now this is where we need to do a little bit of mathematics. And once you do this step, we are essentially done. So here, as you can see, you have epsilon L Ti x xi plus delta x. Here you have a delta x, and then here you have a delta x. So what we will do next is we will convert this in a form where we can do a Taylor expansion. So let's do it. So we have L Ti xi plus delta x. Now, xi plus 1 minus xi over epsilon is simply the velocity. So we can write it as xi dot minus delta x over epsilon. Okay. And then here we can write L of Ti minus 1, xi minus 1, xi minus 1 over epsilon is the velocity again calculated at the I minus 1th point. So this will be xi minus 1 dot plus delta x over epsilon. And then we'll have the two remaining terms, which will be epsilon of L Ti xi plus 1 minus xi. Write it a little bit carefully. Xi now xi plus 1 minus xi over epsilon is again xi dot, and then we have epsilon L of Ti xi minus 1 xi minus 1 dot. Okay, now we have a form which can be Taylor expanded. So let's do the Taylor expansion. The Taylor expansion of the first term will give us epsilon L Ti xi I dot times plus epsilon times delta L over delta X times delta X, plus that's the expansion of the first term here. Then you will get a delta L over delta Xi dot, that's the expansion for this term, minus delta X over epsilon, okay? Plus, let's expand this part where we will get epsilon L Ti minus 1, Xi minus 1, Xi minus 1 dot times plus, that's the first term, then you will get epsilon times delta L over delta X dot delta X over epsilon. So that takes care of the expansion here because there was only one term which has delta X. And now we will have the two terms which were coming from the original part, which is epsilon L of Ti Xi dot minus epsilon L of Ti Xi minus 1 Xi minus 1 dots. Okay, now these two terms will cancel. So here we have L epsilon L Ti Xi X dot. This will cancel, and this part will cancel here. So what do we get? We get change in A is equal to epsilon delta L over delta X times delta X. There's a minus sign here, so we can write this term first. We'll get an epsilon delta L over delta X dot times delta X over epsilon minus epsilon delta L by delta X. Yes, this is I minus 1. This is I by delta X over epsilon. Okay. Now what we can do is we can take the derivative of both sides with respect to delta X, which will give us delta A over delta X equals epsilon delta L by delta X plus this term we can write as 1 over epsilon times delta L by delta Xi minus 1 minus delta L by delta Xi multiplied by epsilon. Okay, because we are already taking care of this delta X. Delta X was divided on the left hand side. Now, what do we have here? Now we have delta L, delta A over delta X equals epsilon times delta L by delta X. Now, here we can actually write it in a different way. We can write it as minus of delta L by delta X dot calculated at the point I minus delta L by delta X dot calculated at the point I minus 1 divided by epsilon. But epsilon is simply Ti minus Ti minus 1. Okay? So since this is the quantity delta L over delta X calculated at the point minus 1 and I and I minus 1 divided by Ti minus Ti minus 1. we can write this as epsilon delta L over delta x minus d over dt, the time derivative of the quantity delta L by delta x dot. Okay, and why is that so? Because the time derivative of any quantity is defined as the difference of the quantity uh, I minus 1 divided by the change in time. So the change in the quantity at two different times divided by change in time. So this can be written as d by dt of delta L over delta x dot times epsilon. Now remember, because of Hamilton's principle, the change in A is going to be zero, right? The, the action is stationary along the original path. So change in A, so delta A by delta x is going to be equal to zero, which means that this quantity has to be equal to zero. Now, epsilon is something that we choose. We can choose epsilon to be non-zero, the way we construct our limit of the sum. So the only thing which remains non-zero in this part is the quantity under these square brackets, which is delta L by delta x minus d by dt of delta L by delta x dot equal to zero. Okay. So using Hamilton's principles, we can say that this quantity will be equal to zero, which is our Euler Lagrange equation. So in this derivation, the only part that matters is conceptually understanding that an integral can be written as the limit of a sum. And once you write it as the limit of sum, then you just need to take care of each part, do a Taylor expansion, and then you will get the solution, which would be your Euler Lagrange equation. So I hope you like this derivation. If you like it, subscribe, hit the like button, and see you in the next video.